So the last lecture taught us how to find our p-value, figure out if we made a discovery or not, and find our 95% confidence interval of effect size, figure out what size that effect is in the population. Today I'm going to put this to use in the context of a two-group between subjects experiment. This is our data, simple experiment. Does studying with music hurt or help grades? Most of my students, and myself included, probably hypothesize that studying with music improves grades. We'll see if that's the case with this data. So this is the data we'll be using today. The two things that we always want is your p-value and 95% confidence interval of effect size. When p is less than 0.05, we know the independent variable influences the dependent variable in the population. Our 95% confidence interval of effect size tells us the population effect size possibilities. Now, before we actually do the analysis, I'm going to talk a little bit about what p is for this test specifically, the specific effect size we use for this test, the t statistic, and the random sampling distribution. This is a math-heavy section. You don't have to know everything. Give it a try. Ultimately, at the end of the day, we're going to interpret our data based on p and 95% confidence interval. But I have to teach you some of this, not necessarily for everybody, but for those of us that may want to go to grad school, and do science. Just a little review on p-value. It starts with the null hypothesis, which is the hypothesis that the independent variable has no effect on the dependent variable in the population. Which, for this case, it's that the test scores for all humans who study with music equal the test scores for all humans who study without music. Music doesn't matter, essentially, is what we're saying, right? Which is a population mean difference. All I did was subtract those two means from each other, those who study with, those who study without in the population. This is important to understand the math. Without viewing your null hypothesis that your population mean difference is 0, you won't understand the math, which is okay if you're not going to go get a PhD and do science. P-value is the probability of obtaining data, quote unquote, like the data the experiment found if the null hypothesis were true. The other three examples are saying the same thing, except they're pointing out, if the null hypothesis were true also means if our manipulation has no effect on our DV in the population, if our IV has no impact on the DV in our population. I use IV and manipulation interchangeably sometimes. If the test scores for all humans who study with music equal the test scores for all humans who study without music, if the population mean difference is 0. Now, what I didn't define in our last discussion was, what do I mean by like the data the experiment found? Well, it's different from each test. So in this case, it means as surprising or more surprising than the data the experiment found in either direction. So for example, let's just say studying with music decreased grades by 8%. What's more surprising than an 8% decrease in either direction? Well, a 9% decrease, a 25% decrease, a 10% decrease, a 200% decrease. Everybody understands that. Yeah, that's more surprising. And what do I mean as surprising or more surprising? As surprising or more surprising than the data we found in either direction if the null hypothesis were true, right? So, we've got to put it all together. So what else is as surprising as that is an 8% increase. The opposite of what we found. That's as surprising as the data we found if the null were true. A 9% increase, a 25% increase, a 10% increase, and a 200% increase. It's okay if you don't get this. You just kind of got to trust me here. It's complicated, the reason why we do it this way. Why don't we just say as surprising in the same direction? It's actually complicated and has to do with the fact that we can't trust humans. Ask me about it in class if you care. Now, Just like last lecture, when our p-value is less than 0.05, our data suggests the null is false, and we have a significant effect. We've made a scientific discovery. Everything I said before holds. P-value greater than 0.05, our data do not suggest the null is false. I know nothing, non-significant. Did I allow a baby to run my research again? Did I use bad science? Or is the null hypothesis true? I don't know. The effect size we use is called Cohen's D. And the formula is right there at the upper right. Mean 1 minus mean 2, those are your two sample means. So in this case, the mean for individuals in the music studying condition and the mean for individuals in the non-music studying condition divided by the standard deviation pooled, which is essentially the average standard deviation across your two conditions. Now, this statistic converts your sampled mean difference into standard deviations. So when my Cohen's D is 1, my two means are different by 1 standard deviation. And you're probably like, what's a standard deviation? That's a great question. I have to explain that. So a standard deviation approximates the average difference from the mean. This is something I want everyone to know. This is really the only thing you have to know for this slide. The other stuff is kind of fun for me. When your standard deviation equals 5, you know that on average scores differ from the mean by 5 units. Now this would be in like your control condition or your experimental condition, not both. Cohen's D is a little unique. Standard deviation is 4. Oh, in my data set, on average, scores differ from the mean by 4 units in my data set, like in your control condition, in your experimental condition. And you see the word approximates the average. Well, there's a reason we're not just finding the average difference from the mean, and that is because the average difference or average deviation, I'm going to start using those interchangeably, that is always 0. So I'm going to prove that to you just in a quick little example. You can run your own separate data example and prove it for yourself in a different data example. But 1, 2, 3, that's our data set. The mean of that data set is 2. The difference from the mean, 1 minus 2 is -1, 2 minus 2 is 0, 3 minus 2 is +1. When we find the average, we want to find the average difference. We have to first sum up the differences. And these differences sum to 0. Well, let's keep going with the average. Divide by the number of things that we're averaging together. Divide by 3. That equals 0. That will always equal 0. The average difference from the mean is always 0. Now, you're probably like, wait, why do we care about the average difference from the mean? Well, that's important. That tells us how spread out our data file is, how spread out our data is. You know, if my data set was 1, 1, 1, you know, I'd have no difference from the mean. Every score in my data set would be the mean. It's something that we use to figure out how much error is in our data, and that'll make sense in a little bit later. Now, what we use is the standard deviation calculation, and it squares the different scores to get rid of this problem where you can really see the problem there. You have negative and positive different scores, and they balance each other out because of the definition of the mean as the center of your data set. So how do you deal with that? Well, standard deviation squares and takes the square root to deal with this problem. Let me show you. Same difference scores, we're starting there. We got to get rid of the negative sign, so we square the different scores from the mean. And then we calculate the sum of squares, which is just the sum of the squared different scores from the mean. So if I sum my squared different scores, I find my sum of squares is 2. Then, well, there were 3 different scores that went into this calculation. Let's find the average squared difference. We give this statistic a name called variance. Variance is the average squared difference from the mean, and that's just sum of squares divided by 3. Now, on average, my scores differ from the mean by 5 squared units. What? That doesn't make sense to a human being. So we take the square root of variance to get standard deviation, and that equals an approximation of the average difference from the mean. I won't ask you to calculate that. I do have a little asterisk on the 3 right there. And that's because In most statistics packages, they don't divide by the number of different scores, they divide by the number of different scores minus one. This is called Betzel's correction, and the reason why they do that is because this allows the standard deviation in your data set to better approximate your population standard deviation. It's complicated. It's not worth knowing, really. I just feel I have to tell you some of this stuff. It won't be on a test. This is for those of us, this section right here until I get to the analysis is really for those of us that are planning to get PhDs and do science. Now, we do have to think about Cohen's d in the context of the standard deviation, because you got two standard deviations. It's a different, like, it's complicated, okay? So what is the standard deviation in the context of the Cohen's d calculation? So earlier it was the mean difference divided by the standard deviation pooled, which I said is just essentially the average of the standard deviations in your two groups. So we need to understand, well, what's the standard deviation in my control group? What's the standard deviation in my experimental group? Let's talk about that. So the standard deviation in my control group is the average amount observations or scores in the control group differ from the mean. And like, you get that. You should get that from the previous slide. And everybody needs to get that. But why do scores differ from the control group mean, right? Like, that's actually important because that control group mean is our signal to the world, like, hey, this is how the control group did. You know, for our studying with no music condition, it's like, this is the average test score for people who study with no music. That's the thing we promote. That's the thing we put in the newspaper. That's the thing we're like, yay, we did that. So we got to ask ourselves, like, oh, why do scores differ from that predicted signal? And also, we want to tell people how much scores differed from that mean of that condition, because that tells us how much error there is in our data set. And going back to my question, why do people's scores differ from the control group mean? Your first answer is probably like individual differences. Yeah, that's true, and we didn't measure those. We don't know why they differ. Maybe it's individual differences in, you know, IQ, math, experience, who knows, lots of things, right? There could be a lot of things that are causing scores in that condition to differ. Attention, interest, a lot of things, right? But we didn't measure them. When we don't measure individual differences, they add error to our data. So yes, individual differences. But in my view as a scientist, it's like, well, if I thought it was an important individual difference, I should have measured it and mathematically controlled for it, which is a super advanced concept I'm not going to tell you about today. All right. But also, like, okay, let's say I wrote some poorly worded questions that, you know, caused people to have different interpretations of what I was asking. They didn't understand the question. Right? Like, in whatever test it was, maybe I had some poorly worded questions that just confused people. Well, that's error in my data, and that's going to cause people to have different scores on that test, right? Or just bad data entry. I let the baby do it. It's, we slipped. I hit 5 when I should have hit 3, you know? It's like, there's a lot of reasons why scores in your control group differ from the mean. But because we don't know what they are, we call them error. The same thing's true for the standard deviation in the experimental group. Oh, why do the observations in the experimental group, why do those differ from the mean, which is the signal we present to the world? Well, it's error as well. Same reason. Our standard deviation pooled is the average of the two previous standard deviations. So really your standard deviation in the context of Cohen's d is the average error in your experiment, right? Oh, the average error in my control group averaged together with the error in my experimental group. So my standard deviation says, oh, on average, there's this much error in my data set, like for the standard deviation pooled. So Cohen's d is just your mean difference divided by the average error in your experiment. So Cohen's d of 1, my two means differ by the average error in my experiment. The cool thing about Cohen's d, it's not on the slide, it probably should be, is that it allows us to compare effect sizes across experiments. So if I run a study on racism and find a Cohen's d of 1 and you run a study on therapy and find a Cohen's d of 2, your study had twice the effect than mine. Your study shows that your therapy experiment, right, changed scores by 2 times the average amount of error in your experiment, while my study shows that my racism experiment changed scores by only the same amount as the average error in my experiment. It's okay if you don't get it. This is how I process statistics. I don't just learn the definition, I think about what it means. So that's what I'm doing here early in the class. I'm processing these ideas with you. At the end of the day, you don't need to know most of this. You do need to know that Cohen's d tells us the number of standard deviations apart our two means are. The number of standard deviations our two means are different by. I do want you to know that. The stuff about error, I think it's important for a budding statistician. I think it's important for somebody who gets confused by math. I often have students tell me they didn't understand stats. And I'm like, well, let's explain everything that's going on in the way that us psych majors talk about things. Like, we talk about concepts, we talk about what they mean. It's not just about the numbers, it's about the ideas here. So we got our standard deviation in our control condition. Well, scores differ from the mean because of error. Standard deviation in our experimental condition. Scores differ from the mean because of error. So if we average those two standard deviations together, that's the average error in my experiment, right? It's just good to think about things like this. Now, this is something everybody needs to know, and it's fine to know this, right? Like, what is an effect size, right? Small, medium, and large. Cohen's d of 0.2 is small, 0.5 is medium, 0.8 is large. And they differ by those many standard deviations. Our 95% confidence interval of Cohen's d tells us our population effect size, or our population Cohen's d, is very likely one of the values in the interval. We got our teacup chart. I might change it. It's coffee for me, though. It's definitely coffee for me, but it looks like it's coffee and teacups. I love it. The bottom line is your number line of Cohen's d's. So these are all the Cohen's d's. Cohen's d can technically be as large as negative infinity, as large as positive infinity. One thing I want to point out is that the strength of a Cohen's d, it's not based on the sign. I didn't put negative 0.2 is small, negative 0.5 is medium, negative 0.8 is large, but they are, all right? And so on the base right there, we have our number line from negative infinity to positive infinity, and we have our conversions. We have a bunch of effect sizes that this can be. We have small, medium, large, right? You have less than small. You have no or null effect, and small, medium, and large, and less than small on both sides, okay? The convention that I use is that positive Cohen's d's go in line with the hypothesis I predicted, and negative Cohen's d's go against the hypothesis I predicted. This is not a forced practice. It's a convention that many of us in the field use, but let's just keep using it in this class, okay? So positive means in line of my hypothesis. Negative means against my hypothesis. So if we go up one more line, you're seeing something here. What's really important is in the middle. We argue the null is true. So I want to focus you there. What does it mean when your effect is less than the effect we consider small, right? Well, that means it's essentially not an effect. If I'm like, this is small, what's less than small? Nothing. Like, this is a small amount of coffee. This is a less than small amount of coffee. That's like nothing. That's practically nothing. It's mathematically a little bit more than nothing, but practically it's nothing. And this is why I love being a psychologist. I can leave the numbers a little bit and talk about this in common sense terms. So one of the things that really should upset you with p-values is that you can't say the null hypothesis is true, right? Why should that upset you? Why should that upset you, excuse me? Because you put your heart and soul into this experiment, and you get your p greater than 0.05, and you're just like, I know nothing. Gosh, that's frustrating. Gosh, it's so frustrating. I want to know, did I run a bad experiment or was the null hypothesis true? Well, if my 95% confidence interval is between negative less than small and positive less than small, right? If it's negative less than small, that's a tiny effect that doesn't matter to me. It's less than what I consider small. It's not important. It's trash. Null effect. Yeah, that's an effect that's tiny. There's no effect there in the population. It's small, right? It's trash, right? There is no effect. My hypothesis that there was an effect was trash. There's a positive less than small. That's so tiny, I don't care about that either. That's trash as well. Well, if your 95% confidence interval of Cohen's d falls in that range, we argue the null is true. That is not trash. That tells me I did my best job and I was just completely wrong. These two population means are the same. My independent variable has no impact on my dependent variable, right? The null hypothesis that there is no effect in the population is strongly supported. The other stuff, right? Well, null is false, null is false. Like, that's just important. That's the discovery piece. This next line is talking about something I said earlier. Positive effects are in line with my hypothesis. Negative go against. Null is there was no effect at all. That's a perfect zero. Like you sampled a mean difference of zero. That would be that's just what that one means. And then for me, when I put it all together, p-value plus effect size, right? With p-value, anything that is positive less than small, positive medium, positive large, right? Anything that's in that range is a discovery, right? When your p is less than 0.05 and your hypothesis was supported with your data, we'll get to that in a second. We don't know if our effect size is positive, less than small, positive, medium, positive, large, right? But then we look at the 95% confidence interval of Cohen's d, and we're adding that extra bit where that negative less than small and positive less than small are kind of not really important, not really real. Those are not discoveries. So when we put them both together, right, we have a little bit stricter criteria for discovery than p-value alone. We're like, look, my p-value less than 0.05, that's a discovery if my 95% confidence interval of Cohen's d does not include either of the less than smalls or the null. Just use this chart, print it out, practice it. Maybe that was a little confusing. I'm not trying to make it confusing there for you, but this is the way I think about everything together is that top line, my p-value and my 95% confidence interval. I'm happy when my data show that the population effect size is between small, medium, and large. I'm not happy if I have a significant effect, p less than 0.05, and my effect size could be positive less than small, positive medium, or positive large. And this is just kind of part of the new world we're part of. Now, in your lab, they focus only on the p-value statistics, so just kind of, you're going to have to navigate that for yourself. My advice for any budding statistician or any budding scientist is go Google things. Go Google things about p-value and effect size. You can find Daniel Lakin's blog and learn so much more if you're curious. But I'm going to go on for those of us who aren't curious. Sometimes I get stuck in the clouds. I'm definitely there right now. All right, so the independent samples T statistic is the thing that they teach in stats class, and they starts you off there. And I like to break statistical calculations down. So you see that formula over there that looks like, the formula for time travel. Let's just break it down so it's not so scary. First thing I want to say about this is that the T statistic gives us the p-value that allows us to conclude that our population mean difference is not zero, right? If we get the p-value, you know how to do p-value, right? If p is less than 0.05, my IV has an effect on my DV in the population, right? In this case, my two population means are not the same, so my population mean difference is not zero. That population mean difference is not zero is important for the math nerds, but you already know P. So we use the T statistic to get P. Those of you that hate statistics, don't want to be PhDs, I totally feel you. You can go past, you can skip the next 2 slides. I wouldn't recommend it just because you won't know what's going on, but I feel you, all right? I feel you, and I want you to know that this is all you need to know. We use the T statistic to get the p-value. That's all that's important, practically, for us. But for those of you that are curious, I'm going to describe it, and it's going to take me a little bit. So either fast forward or bear with me. That formula, you look at the numerator, the top of the division line. The first thing you see is those 2 X's with bars over them. Well, that's your sample mean of your control minus the sample mean of your experimental condition. Really, it can be either or. Your sample mean of your experimental condition minus your sample mean of your control condition. Doesn't matter. That, you can see it's bracketed together, telling you it's 1 unit, so that's your sampled mean difference. So it's your sampled mean difference minus, oh, what's this other thing? That's another difference. And that's the difference in population means that is predicted if the null hypothesis were true, right? So you have your sampled mean difference minus the predicted mean difference if the null hypothesis were true. That second unit, that second part of that numerator is always 0, and people like lop it off. But that then ruins the conceptual understanding of what's happening. You are seeing how different your sampled mean difference is from the predicted population mean difference of 0 if the null were true. So that's cool. That's what the numerator is telling us. We're figuring out how different our experimental result is from the predicted result if the null were true. Then you divide by, and that equation does not have a conceptual meaning or understanding. That equation was derived by hard work by our statistician friends that are good at things that we're not good at. That bottom part is called standard error. And so I'm going to define that in the next couple of slides, but I just want to say we find a T statistic of 5. What do I know? My experimental result, or your experimental result, or hey, we're working together, our experimental result. Our sampled mean difference in our experiment is 5 standard errors greater than the predicted mean difference if the null were true. And I kind of define that. The population mean difference in the imaginary world where we assume the null hypothesis is true, which is always 0. All right. What's a standard error? It's a standard deviation in the random sampling distribution. What's the random sampling distribution? Let me show you. Remember, folks, if you're not interested in the PhD side of this, you can skip forward this slide and the next slide. The random sampling distribution is the imaginary world where the null is true stated in math. Like not only stated in math, then graphed from the math. And we get p-value and standard error from this graph. So let me just show you this, okay? You're like, well, okay, I said this is a distribution that assumes that imaginary world where the null hypothesis is true is the case. So let me just tell you what it is. First thing you look at a graph, what's on the x-axis, which is the horizontal? Those are T statistics, right? So T statistics are just a way to convert your experimental result to a number of standard errors different from the null. It's sort of like saying my experimental results plus the null hypothesis gets me my T statistic, okay? But the way I view it is these are just all possible mean differences I could sample. What you don't see on my graph is that it goes from negative infinity to positive infinity, because it basically just looks like a little line from to negative infinity to positive infinity. So it just kind of keeps flattening out. But that's important because this distribution tells us, well, this distribution allows us to understand any experimental result we could obtain from negative infinity to positive infinity if the null hypothesis were true. So, but on the x-axis, those are your t-scores, which are your potential experimental results. Anyone you could get in an experiment. Now this density, it's labeled density, that means probability, okay? Just trust me there. If you're in a real stats class, you know I'm basically right. And I could be a little not being specific enough. But essentially what you can see here is when the curve, that blue line is higher, that event is more probable. So I said earlier that this is the random sampling distribution. that this random sampling distribution was set up so that it's the imaginary world where the null is true, right? Well, in that imaginary world, the most commonly sampled mean difference is 0. And if you look back at the formula, the T statistic you will get when you sample a mean difference of 0 is 0. You can see that that is the most likely experimental result you can find. Okay. Let's keep talking. As you move further and further away from 0, right? Well, let's say when you're near 0, but not at 0 explicitly, you still have experimental results that are very likely. These are very likely experimental results. But then we move away from 0. We move to like 0.5. Less likely, but still, you could get it. We move to 1. Less likely, we could still get it. We move to 2, and it's like, oh, that T statistic of 2 in this example seems unlikely. Very, very unlikely, you know. Now, this is not a heuristic. Do not go there and say T's of 2 are always significant, because these random sampling distributions change based on the experiment you're running, and I can talk to you about that if you want in office hours, but I'm not going to talk about it in this lecture. So first, I want to say the standard error is the standard deviation of all these potential results in this distribution, and that's all I'm going to say about it. That this is in this distribution, this probability distribution, that tells us the probability of sampling any experimental result from negative infinity off the screen to positive infinity off the screen, if the null hypothesis were true, is the random sampling distribution. The standard deviation of these potential results is your standard error. Okay? That's it. So let's talk about how we use this to get P. We run an experiment. We calculate a T statistic. Well, first, we do that. But before that, I gotta give you a little fractions lesson. So this curve, let's close it up. Because really this is, underneath this curve, the area underneath this curve is one whole. So one whole, right? Or 100%. So I'm closing it off for you so you can see that in your mind. Because our p-value, our p-value is a probability, our p-value is a percentage of this whole. So I need you to realize that. I like to go back to 4th grade where every fractions problem was a pizza. We have a bell-shaped pizza, okay? We sampled, like I said earlier, we ran an experiment, our T statistic was 2. And we want to figure out the probability of sampling an experimental result that is as surprising in either direction as our sampled result of 2. Well, either direction, a negative 2 is as surprising as a positive 2. All right? So we need to find the probability of getting results that are as surprising or more surprising than the result we found in our experiment. That's where p-value comes from. That percentage of the bell, let's say it's 2%, divided by 100, our probability is 0.02. This is where p-value comes from. So all that stuff where people had you use those tables, or, you know, I don't know what your other stats classes did, but I can just go back to mine. Using those tables, finding those area beyond the curve, multiplying by 2. This is all you're doing. You're finding the probability of sampling an experimental result, in this case a mean difference, which we convert to a T statistic. So in this case, a T statistic that is as surprising or more surprising than the result we found in our experiment in either direction. That's your p-value. So we're at our summary now. Those of you that didn't skip, here, like, I'm going to simplify this. What do we need to know? Our T statistic gives us our P. P less than 0.05 is significant. Those are all my, like, what do we know? Our data suggests the null is false. Our data suggests our IV impacts the DV in the population. Our data suggests our population mean difference is not 0. P-value greater than 0.05, I know nothing unless it's accompanied with a 95% confidence interval between negative less than small and positive less than small. Then I know the null's true. It's not on the slide, but hopefully you write that down. Cohen's D is the effect size, number of standard deviations apart, small, medium, and large are on the screen. 95% confidence interval of Cohen's D gives us the population effect size, which we will convert to small, medium, and large, and talk about it that way. Okay? We don't write it up that way. You'll see how this all goes down. We use a program called Jamovi for data analysis. It's actually a pretty awesome program. It's free. It's free if you download it onto your computer. So you download the program from Jamovi's website, jamovi.org. Google will lead you right to it. There's something I got to say during this class. If you have a computer that is full of viruses, get rid of them. I can help you, but I provide no warranties, right? When I have a computer that's full of viruses, I wipe it clean and reinstall the operating system. This is why I have 12-year-old computers that still work. So you can do that for Windows. You can do it for Mac. If you're really nerdy, you might want a Linux operating system. Or if you have an old computer that's slow, put Linux on it. These are all things I can help you with during office hours, but that's mostly me being kind, okay? I like computers. I mess around with them. I build them. Like, I can help you here. But I'm going to tell you something. If your computer is trash and you have 900 videos on it or no space left, you can't do your work. Even me, I get in this situation where it's like I got 500 windows open and my computer's trash and it slows down my work. So this is my New Year's resolution, is to do this myself. But don't just be okay with your computer being trash. Learning how to install an operating system is not rocket surgery. You can figure it out, but you need to do it. Please try to download Jamovi for a class, but if you fail, I'm here for you. I get it. You got to understand it took me years of taking apart electronics and Xboxes and stuff before I really understood computers, okay? So I'll help you, but please try to download this program for class. It should be something we can do, and if you can, it's probably due to the fact that your computer needs a little love. So when we enter our data, there's two things I want to point out. First, a row is horizontal and columns are vertical. Okay, so when I say row, I'm talking about going across the screen. When I say column, I'm talking up and down. So we have two columns, one for our independent variable and one for our dependent variable. Our independent variable is the music condition. Our dependent variable is test scores. When you name these variables, do not put any special characters like a space anywhere in that name. Just, okay? You could have called it music and test, right? Or music and scores. I like to write things out. So I need you to enter your data this way. A lot of folks enter their data with numbers. They put numbers in there, and I'm not doing that. Like, I'm putting in my data so that it makes the most sense to me. So I can see who is in the music condition, who is in the no music condition. So I can just type those in. And then my test scores are all presented right there. That's the dependent variable. So I entered my scores just like this, one row per participant, right? So each participant only gives us one score. So because this is a between subjects design, they're only in one condition. So we're good. Now, if you double click on the variable name, music condition in mind, you can change the name to whatever you want. You want to change that measure type to nominal. Nominal just means that the variable, the different variations in the variable, the different options in the variable differ by name only. Okay, I don't know which one's better or worse. I just don't. So we'll just hold that there. And then over there in the levels condition, I moved music to the top because I predict that participants in the music condition will get larger scores than those in the no music condition. All right. But this is important because it'll mess up your sign of your Cohen's D. So if you predict that no music will do better than music, go ahead and move that up. It's not my hypothesis, it's your hypothesis. In fact, you can do that because that hypothesis probably makes a little bit more sense than studying with music if you think about it. So just make sure for your nominal variables that you order them in the way you're predicting the result to come out, or your main result to come out. Do the same thing for the test score variable. Double click it. Make sure the name has no special characters. It's a continuous measurement type, which means that as the numbers go up, as the test scores go up. That's all it means. Continuous. The numbers keep going up. That's all. Use a continuous variable when you have a numeric DV, essentially. The first thing that is super important before you look at P, before you look at 95 CIs, is to just graph your data, look at it some way. They're going to show you different ways, descriptives in lab. Go ahead, play around with that too once you learn that. But essentially here, it's the most important, it's a very important first step. Look at your data, see what's going on, get your head right. In order to do this, you have to have add a new module to Jamovi called FlexPlot. You can see that big plus module sign. You're going to click it, and you're going to add the FlexPlot module from the Jamovi library. I'm not going to tell you every step, though. You got to understand that I learned a lot of computer abilities by just clicking things around. So I'm going to send you in the right direction, but I'm not going to tell you every step because I want you to think. Nothing will happen if you hit the wrong button. If you really get stuck, I'll help you in class and I'll get you set up. But add the FlexPlot module to your Jamovi. Click the plus module. You'll see there's a Jamovi library. Try to find the add-on. If you can't, you won't be able to do the graphing yet, but that's okay. You can skip that for today if you mess up. So now after we've added the FlexPlot module, click FlexPlot, FlexPlot. Okay, analysis, FlexPlot, FlexPlot. Super easy. You'll see this isn't the whole screen that pops up. This is the upper left-hand side that pops up. You need to move your dependent variable to the outcome variable. Those are synonyms. Write them down. Okay. Predictor variable is your IV. You move your predictor variable there as well. That's it. That's it. You'll see you'll have a graph. But there's one more thing I want you to change. Go down to this fit options option. Click this little arrow right next to the phrase fit options. Change your center spread to mean standard error. I think the original one is median standard deviation, but if you don't change it, it's not the end of the world. This just is more in line with what we publish in psychology, but it's not the end of the world if you don't click this. I don't even really care. Well, I'll show you what I care about in the next slide. So we get a graph like this. Those little gray dots are our data points. The first thing I'm looking for is, bad data entry. Did I enter impossible numbers? No, these are all possible. Next thing I'm looking for is outliers. Is there something that just doesn't seem right? Somebody that totally failed the test, got a 0%, Well, there's that person who scored 95, but that's not an outlier. That's just a good score on a test, So that's the closest thing we have to an outlier. I don't see that. It's not an outlier. So the no music condition. In the music condition, all the scores are kind of bunched together. There's nothing going on there. I don't see any impossible scores, no outliers. So, I'm just checking. I'm looking okay, this is all good. And then I'm like, well, what do I see in the pattern? So those two red dots are the means. Those little whiskers are plus or minus a standard error, which really doesn't mean that much, but it's what we graph in the field. And I can see that studying with music harmed test scores. So I was wrong, which is pretty much par for the course in my science. But yeah, it happens. Being wrong is okay if you can keep running experiments and keep figuring it out. So this is a realistic example. I was wrong. But now I need to get my p-values and all that stuff. I click Analyses, t-test, Independent Samples t-test. This will pop up. I have to pull and push or whatever you highlight and push it over. My test scores to the DV box, my condition to the grouping box. We are running a student's t-test, right? So I have that clicked. That's naturally clicked. If you look at the click blue box option. I also want my effect size and 95% confidence interval of effect size and my descriptives. The other stuff doesn't really matter. Once I click that, you will see all of these statistics. It's all done for us, right? And that's the beautiful part here. I don't have to calculate anything. This is great for us. I hate doing calculations by hand, and I mess them up all the time. So now my T statistic is negative 5.6. I'm going to round up to 1. And that means that my experimental result my sampled mean difference, is 5 standard errors lower than the predicted mean difference of 0 if the null were true. Degrees of freedom, that is for a between subjects t-test is number of participants minus 2. So we had 10 participants minus 2, that's 8. It doesn't really matter. It's a throwback to 50 statistical calculations, but we still have to write it up. I'll show you in a second. P-value is at less than 0.05. Don't use the heuristic where you just see an O and a 5. There are 3 O's there and a 5, so it's 0.0005, okay? Cohen's D is massive. I do this a lot. I make the data kind of nice and big. Our Cohen's D, that first one, that effect size of negative 3.55, that's the Cohen's D of our sample, right? That's our sampled mean difference. So that's a large sampled effect size. The population effect size is in the 95% confidence interval of effect size. So our 95 CI of Cohen's D ranges from a negative 6.18, which is negative, my hypothesis was wrong, 6.18 large effect, to a negative, my hypothesis was wrong, right? 0.86, also a large effect. So I know my population effect size is between negative large and negative large. I know I was wrong, and the effect size is large. Now, the descriptives gives us the mean and standard deviations for our 2 groups. This is important because we have to write it up. When we write this up to the world, we're like, oh, there's about an 8.2% reduction in test scores when you studied with music. That's big. It's made up, so you can still study with music, right? We can see that because those 2 means are differ by that much. The standard deviation in the music condition tells us that on average scores differ from that mean of 82.8 by 1.92 units on average. On average scores differ from the mean by 1.92 units. In the music condition, in the no music studying condition, they differ by 2.65 units on average. Now, challenge question. This is my hypothesis, but what if I predicted that the music condition would study worse? Well, then you would have been right, and so then your test statistic needs to be positive, your effect size needs to be positive, all your effect sizes need to be positive, they all need to shift signs. Do you know how to do that? It's back to how you entered your data for the music condition. Hint, hint, arrows, arrows. Now, for those of you that are just trying to survive the course, this is the correct answer. All that data, all that analysis, this is the correct answer. First, you have to mention both groups, their means and standard deviations. Is it significant or non-significant, the effect? What's the population effect size? So, studying with music significantly reduces grades compared to studying without music. If you notice, I skipped over the numbers. I'm going to go back to those numbers. Studying with music, M, parentheses, M, right? Italicized. That means mean, equals 82.80. Only put your results to 2 decimal places most of the time. I'll explain the one time you don't. Comma, standard deviation, italicized, equals 1.92. Same thing for the other mean and standard deviation. Look at the M and the SD. They're always italicized. All statistical abbreviations are italicized. And we report our data to 2 decimal places for nearly everything. I put a semicolon in here. Some people put a colon. Some people put a comma. It doesn't really matter. Like, there aren't grammar rules for how to start putting a bunch of numbers at the end of your sentence. All right, italicized T with 8 degrees of freedom equals negative 5.61. Right, we talked about what that meant earlier. Comma, p-value, this is the thing you can go to more decimal places because people were cheating and saying they found significance when they didn't. So, like, yeah, they were cheating. So we report our p-values all the way out now. Cohen's D and 95 CI of D are presented right there. You'll notice that I put the Cohen's D that with the lowest magnitude, not the most negative Cohen's D, has my first Cohen's D with, my larger Cohen's D being my second one in terms of magnitude. The other way hurts my brain. Both ways are technically correct, so I'm not going to take off for that. And then I just say the population effect is a large effect. The one thing I want you to realize is that these 95% confidence intervals of Cohen's D are a response to things in our field that are just not too pleasant. Essentially, it's kind of a new way to do it. When we discovered that p-values didn't lead to truth that often, we started requiring these 95% confidence intervals of Cohen's D so that we could interpret our own data a little bit better. So then I just put the sentence in at the end. The population effect is a large effect. Now, if you can work your sentence differently, I'm happy. Language and writing, I'm just going to admit it. It's not my strong suit. My strong suit is nerd stuff like math and experimental design and having fun, right? So if you can write this in a more concise way, hey, show me. But yeah, and then I got a few the things I said earlier are down there in those bullet points. There's something that I think is really important, but they don't teach in the lab. So I'm kind of a little pulled. When you run a test, you're supposed to check its assumptions. Assumptions are like requirements to use the test. For a between subjects t-test, we're supposed to have normally distributed data, even though people debate that. We're not getting into that debate. And we're supposed to have a quote unquote equality of variance, which is equal standard deviations in your two conditions. That's all. So those are the two assumptions we're supposed to meet. There are other assumptions that are just like between subjects design, no outliers. We've already checked all that stuff. Now, if you violate the homogeneity of variance assumption, Jamovi will give you a warning. You'll see it. And then you can use Welch's t-test, which makes no assumption of equality of variances. Daniel Lakens, who is my favorite living quantitative psychologist, suggests we should always use Welch's t-test. So instead of clicking students, you should click Welch's. I'm fine if you want to do that. Yeah, just kind of let me know in the write-up. But ultimately, that's not what the field does. The field kind of, because we're psychologists and we're not as good at math, maybe as like a physics major or something like that. Like, we often violate things that other fields wouldn't violate. And that's kind of embarrassing when you talk to a statistician. So I just want you to know that. But that's one thing we can do, right? But we often just report the student's T. And Daniel Lakens wrote a whole paper on that. It's really interesting if you like quantitative psychology, which I might be the only one. So that's cool. The Mann-Whitney U test has no assumptions. I'll give you an idea of conceptually what it does. So it takes your DV column and it ranks them from smallest to largest. So 0 is your smallest, 1 is your next smallest, 2, 3, all the way up to the number of dependent variable results you found. It gets complicated when you get the same DV for multiple people and stuff, but what it does is it takes away the potential for outliers or non-normal data, and it just says, okay, let's rank these from smallest to largest. Let's replace the DV with largest to smallest ranking. We'll run basically a t-test on that. Now, the Mann-Whitney U test has no assumptions of equality of variance or normality because it handles all that. But that ranking process just makes that irrelevant. What I do is in my own data, I run a Mann-Whitney U to check my assumptions because it's the easiest, fastest way I can do it. And, I see if my p-value interpretations match. That's all I'm looking for. Okay, this is complicated. The Bayes factor. Remember in class when I wrote the probability of the data given the null hypothesis, right? Well, Bayesian statistics finds the probability of the hypotheses given the data. You really do want to test your hypotheses, right? That's what you want to do. You want to test your hypothesis or your hypotheses if you have one or two, right? This is a completely different way to do stats than we teach in our stats classes for life sciences or that I'm even teaching here. This is the only time I'm ever going to mention it. But this is also the future of stats, and I need to study it more, and you probably do too if you want to be a PhD. But ultimately, it tells you the probability of your hypothesis being correct, not the probability of the data given the hypothesis. So it actually makes more logical sense. It's just super difficult. The Bayes theorem, people were trying to figure that out for, I think, hundreds of years. Bayes, who discovered it, died, And his notes were just kind of chilling and nobody understood it. And then in the 50s, I think people started to understand it, and we're only starting to make statistical tests that allow us to use it. The Bayes factor is one of those. So this tells you that if your Bayes factor is 4, it tells you the probability of your alternative hypothesis that there is an effect is 4 times more likely than the probability of the null hypothesis that there is not an effect. So that's it. This does feel like a little bit of a long lecture. The next one will probably be super short. I went a little slow, and I did cover some statistical topics you asked me in class. I wanted to make sure you had those. Now, I am going to try to move forward in my videos a little bit this semester for y'all so you can get ahead if you want. But that's it. What you need to know how to do, not that last slide with the assumptions, that was for fun. You need to know how to get your analysis, so your graph and your write-up. That's what you need, okay? And that's it. That's what you need to do for the test. I'm going to give you data. I'm going to say, give me a write-up. That's it. All right. Good luck, y'all.